So, hi, Assalamualaikum. My name is Muhammad Hazim bin Adan. My mention number is B1224100034. Our introduction part A. Rectifier is an important part of electronic circuit. Its main job is to convert alternating current which change direction into direct current, which flow is only one direction. This process is essential because many electronic devices need DC to work properly. At the heart of the rectifier is a diode, a device that lets current flow in one direction and block in the other. This helps change AC into DC. This assignment explores two main types of rectifier. The first one is the half wave, and the second one is full wave rectifiers. It's look at how they work, how they are designed, and where they are used. The goal is to understand their role in modern electronics, where efficient power conversion is key to better performance and technology development. So I want to explain the theoretical overview of half wave rectifier. Convert AC to DC using one diode. Allows only the half of the AC cycle, positive or negative, to pass. The common component is AC source. The second one step down transformer, load resistor. The operation is positive half cycle, diode is on to current flows. The negative half cycle, diode is off to no current. The output is pulsating DC with higher ripple. Efficiency max 40.6%. Peak inverse voltage PIV equals to Vmax, important for diode selection. The full wave rectifier is convert both value of AC into pulsating DC. Higher efficiency and smoother output than half wave. Efficiency up to 81.2%. Ripple frequency twice the AC frequency. Two main types of full wave rectifier is the first one is center tape rectifier. Use two diodes and a center tape transformer. The second one is diode conduct during one half cycle. Output is undecretional. PIV equals to times VMA. The second one of two main type, bridge rectifier. Used for diodes, no center tape needed. Two diodes conduct during each half cycle, more compact and adaptable. Use PIV equals Vmax. The practical application is rectifier type half wave rectifier is the application signal demolition, extracting original signal from modulate carrier. The second one is peak detection, identify maximum signal amplitudes. The advantage is simple design, cost effective. The type rectifier second one is full wave rectifier. The application is power supply system for computers, television and chargers. The advantage, high efficiency, smooth DC output. Comparative analysis. For half wave rectifier, efficiency 40.6%, simple and low cost design. Output has high ripple and low average voltage. Need extra filtering, suitable for basic low power application. For full wave rectifier, efficiency 81.2%, produce smoother higher DC output, lower ripple, better performance, more complex and costly, used in demanding or sensitive circuit. Conclusion for part A is half wave and full wave rectifiers are both essential in converting AC to DC. The half wave rectifier is suitable for simple low power applications because it is easy to design and cost effective despite its lower efficiency and higher ripple and contrast. The full wave rectifier is better for high performance system, offering higher efficiency and a smoother DC output. Choosing between the two depends on factors such as cost, circuit completive and specific needs of the electronic system to ensure the best performance. That's all for me. Thank you.
Today I will talk about the analysis of two key transistors, one using the 2N3904 BJT and the others with the 2N5454 JFET. We will cover their operating principle, critical calculations, and simulation validation to understand their behavior in real-world applications. This is our simulation 2N3904 BJT from Multisim, and also this is our simulation 2N5454 JFET from Multisim. This is our calculation BJT transistor. First, we need to calculate base voltage VB. The base voltage is determined by the ratio of R4 that has value of 6.8 k ohm to the total resistance of this divider network. Below is our calculation of base voltage and simulation for Multisim. Next, we need to calculate emitter voltage VE. The emitter voltage is the base voltage minus the base emitter junction voltage drop, which is typically 0.7 volt for silicon BJT, like the 2N3904 transistor. The below is our calculation and simulation for Multisim. After that, we need to calculate emitter current IE. Using Ohm's law, the emitter current is calculated from the voltage across the emitter resistor RE, which has value of 680 ohm. The following is our calculation and simulation. Next, we need to calculate voltage across collector resistor, VRC. The voltage drop across the collector resistor is due to the current flowing through it. Since IC is approximately to IE, we use IC equal 1.985 mA, which has the same value with IE. The following is our calculation and simulation. Then we need to calculate collector voltage, VC. The collector voltage is the remaining voltage after the drop across resistor from collector RC. It tells us the transistor is operating in its active region since VC is greater than VE. The below following is our calculation and simulation. Furthermore, I will explain the calculation JFET transistor. First, we need to calculate gate voltage Vg. The gate voltage Vg is the electrical potential at the gate terminal of the JFET with respect to ground. The following is our calculation and simulation for multisim. Next, we need to calculate gate source voltage VGS. Gate source voltage VGS is the voltage difference between the gate and source terminal of a JFET. The following calculation is expressed in terms of drain current ID so that we can get the value of drain current ID later. The diagram shows the difference of N-channel and P-channel JFET transistor. After that, we need to calculate drain current ID. Drain current ID is the electrical current that flows from the drain to the source terminal in a JFET transistor. So we need to rearrange our algebra equations, and we need to use formula method to solve our algebra expression, and we can get our value of S is 10.8 milliampere or S is equal 3.28 milliampere. So we decide to take the value of X is equal 3.28 milliampere as 10.8 milliampere is too large to maintain our circuit. And the following is our simulation. Last, we will calculate drain to source voltage VDS. Drain to source voltage VDS is the voltage between the drain and source terminals of a JFET that influence the device operating region. The following is our calculation and simulation. I will explain the result of characteristic graph for both BJT and JFET transistor. Both circuit BJT and JFET demonstrate stable operation in their respective active regions. The BJT characteristic graph in amplification, while the JFET voltage control behavior makes it ideal for high impedance applications. These principles are foundational for designing amplifiers, switch, and signal processors. I will let my teammate Abdul Malik to continue our presentation.
Hi, my name is Muhammad Abdul Malik, and I want to present about our discussion. Our discussion has two parts, part A and part B. First is part A. Part A is rectifier analysis. Rectifier are essential in converting AC to DC. There are two main types: we study half wave and full wave. Half wave rectifier, this design use only one diode. It's simple and cost effective, but it has low efficiency, around 40%, and high ripple output. It mostly suitable for low power, non-critical application. Second is full wave rectifier. Full wave rectifier, this can be either center type or bridge type. It utilize both half of the AC signal, resulting in smoother DC and much higher efficiency of 81%. However, it's more complex and is expensive due to extra component. Choice factor when selecting a rectifier, factor like cost, output, quality, and circuit complexity are important. Designer must also consider PIV, peak inverse voltage of the diodes, which affect component selection. Next is part B, transistor analysis. Transistor analysis, there are two types, BJT and JFET. BJT 2N3904, this is a current control resistor with low input impedance. It's ideal for high current switching but prone to loading effect. Our simulation show errors up to 5%. About JFET 2N5457, in contrast, this is voltage control and high input impedance. It works well in low noise, low power circuit with much lower error, just 0.91%, but it needs conservative biasing. Simulation inside using multisim, we observe that real world factor like resistor tolerance can reduce precision. However, results were still closely aligned with theoretical models, giving us valuable insight into practical circuit design. So, conclusion. To conclude, this assignment help us understand electronic circuit better by comparing different types of rectifier and transistor. We saw that half-wave rectifier are simple but less efficient, while full-wave rectifier offer better performance for advanced system. On the transistor side, BJT is suitable for high current application despite some simulation error, while GFET excel in low noise environment with precise setup. Simulation using multisim emphasize the impact of real-world factors like resistor tolerance, showing us how build more reliable system. So, this is our reference. And that's all. Thank you.